Hello everybody, today we're going to learn about atomic absorption and emission, and we'll be using that to figure out what stars are made of and how old the stars are. It's going to have to do with the electron, and so that's why it's related to this chapter that we're on about atomic structure. So where did the elements come from? Let me just preface this by saying I am not an astronomer, I am not an astrophysicist, I am a chemist. This is just a specific example that the state wants us to make sure that you are aware of. So I'm going to be giving you an example and tying it into the chemistry that we're learning, because that's what this class is chemistry. So I'm happy for you to ask me questions. But if they start bordering on more of the astronomy side of things, I'll just be very honest that I may not know the answer. I will know the answer to the chemistry parts, but not necessarily to the astronomy parts. Okay? So a really brief overview of how we even got stars in the first place. So this is all based on the concept of the Big Bang Theory. Okay? This timeline is not to scale. At the very beginning, we have basically nothing. Big Bang happens, time begins. All of a sudden, the entire universe starts to expand really fast. And when things go really fast, they're very hot. And so the entire universe is filled with a really hot, what they call soup of electrons, quarks, and other particles. And it's so hot that we can't even have atoms form yet, because the particles are not even going to get close enough together for them to actually come together. So what has to happen is all of a sudden things start to cool down. And once they start to cool down, then these particles can start clumping together. And we have these little tiny things called quarks. They start clumping together, and that's what makes our protons and neutrons. Believe it or not, protons and neutrons are actually made of smaller particles. Okay? So they're able to form because they slow down enough that they can start clumping together to make the particles that we're used to thinking about. However, it's still way too hot to form atoms. So all of that happened in 1 second. Okay. The next step, where we still have this very hot, what they call fog, that's no light can get through, we still don't have atoms, that lasts for about another 3 minutes. And then if you look, this is 300,000 years, the next part. That's when the electrons start combining with the protons and neutrons to make the atoms. Things are finally cool enough for that to happen. And so they start to clump together and they make the smallest elements that we have, and that's hydrogen and helium. Then 1 billion years goes by, gravity kicks in, and gravity starts making the hydrogen and the helium condense together, and that's what starts making the stars, is the hydrogen and the helium clumping together. And then the stars start to make galaxies. Then 15 billion years goes by, and those galaxies start to cluster together. The stars start to die. They've used up all their fuel, and when they use up all their fuel, they implode. And then they send all their brand new elements that they've been making during their life cycle out into the universe. And then those elements start to clump together and make stars and new planets. So I like this. I feel like this is a little bit more digestible than that big giant timeline. So we have the Big Bang. Everything is super hot. It starts to cool down. We start making hydrogen and helium. They start clumping together to make the stars. The stars burn the fuel in what's called nuclear fusion. They're starting to use up their fuel, and elements get squished together in the process. So we're fusing them into bigger elements. So hydrogen fuses with another hydrogen, and it turns into helium. And then those can start fusing in different combinations, and you can start getting carbon and nitrogens and oxygens. Those start fusing together, and you can start getting some metal atoms that are even bigger. And by the time the star is out of fuel, it's made a whole bunch of new elements while it's burning up all its fuel. And then once it's finally done, it implodes, and then it sends all of those elements out into space. And when that star dies and explodes, we call that a supernova. So I love this picture because it shows you that we have the hydrogen here, and it starts fusing together to make helium, and then it starts fusing together to make carbon. Those start fusing to make oxygen. It just gets heavier and heavier and heavier and heavier. And so what ends up happening is the core ends up very, very dense, and it ends up being the heavier metal atoms in the middle. And then eventually it runs out, it becomes unstable, and then that's how we end up with these implosions. And then if you've ever seen those really pretty pictures of the nebula, right? I don't know if you've ever seen these before. These are those clouds of elements that are just floating around in outer space. Okay. So now we kind of know how the elements, ended up in the stars. We know that as the star gets older, you get more elements present in the stars. And so now we can start to ask, well, how are we going to know which elements are in there? We obviously are not at the star. We can't go there and take a sample from it, right? So how do scientists look at the stars from very, very far away and figure out what's inside them? Well, what we're able to do is we're able to analyze the wavelengths of light that are being absorbed or released by the stars. Those wavelengths of light are going to be very unique, and we're going to be able to figure out what elements they are based on the unique wavelengths. So to understand where the light's coming from, we have to understand something called absorption and emission. So if we have an atom in its normal state, the electron is in the lowest energy level possible. We put energy, like heat, in. The electron gets boosted up into an excited state. It gets pushed to a higher energy level. It does not want to be in that higher energy level, does it? We have Aufbau's rule, which says that the electrons want to be in the lowest energy orbital possible. So if you push this to a higher energy level, it's not going to want to stay there. So what ends up happening is it comes back down to its original level. And in order to come back down, it has to get rid of all that extra energy you gave it. And if we're lucky, the wavelength of energy will be in the form of light. It might be in a different form of energy, like heat, but a lot of times it's going to come out as a light. So you can draw this lots of ways. You could draw it like a Bohr diagram with the energy going in, showing that the electron goes up. Or you could show the emission with the energy coming out and the electron coming back down. Or you could draw it like this, where you're drawing kind of like one level down here and one level up here. I don't care which way you draw it. As long as you tell me if it's absorption or emission, as long as you tell me if energy is coming in or out, as long as you show me where the electron started and where it ended, that's what I'm going to care about, okay? So it doesn't really matter to me which style of graph you show me. One thing that's important to know is that the energy spectrum is huge, okay? Our wavelengths can be really, really small with lots and lots of energy, or our wavelengths can be really, really big and really, really slow, low energy, okay? The visible range is only a teeny, teeny, tiny section of this. So if our energy coming out of our emission process is too low, we won't be able to see it with our eyes. If the energy coming out is too high, we won't be able to see it with our eyes either. Only certain elements will release certain colors that are of energy in the visible range here. Okay, so if you don't see the energy being released, that doesn't mean it's not being released. It just means it may not be visible to our eyes, and we may need like some kind of a machine or device to measure the energy coming out if it's not visible to our eyes. One thing that you do have to know is that red color light is the lowest energy and purple or violet light is the highest energy. And so the nice thing is it goes in rainbow order, doesn't it? Red, orange, yellow, green, blue, purple. So hopefully that's easy to remember. You just have to know that red is low energy, purple is high energy. The way I was always taught to remember it is that red has 3 letters, like the word low. Purple has more letters, right? So that's the high one. That doesn't work for you, think of a different way to remember it, but you should know the order. So if you have a little bit of energy coming out, it means that your orbitals were very close together because it didn't take much energy to get to the next level. If you have a lot of high energy come out, right, if you have something like purple light coming out, that means your energy levels are really far away from each other because it took a lot of energy to get all the way up there. And so it's going to release a lot of energy coming all the way down. Okay? The thing that's really interesting is that because all the elements have a unique combination of the number of protons and the number of electrons, all their energy levels will occur at unique gaps. And so the absorption and emission process will result in a unique set of wavelengths for each element. Remember that the light is coming out on the emission process. The light has to be released and sent out for our eyes to see it. Okay? Some elements only have a couple of lines that we can see, like hydrogen. Neon has a few more. Neon's a little bit bigger. There's more electrons. There's more energy levels for them to move up and down from, so we get more wavelengths. Iron, look at all of these. Iron has so many electrons in all sorts of orbitals, moving all over the place, so we get lots and lots of lines. Hydrogen will always look like this. Neon will always look like this. Iron will always look like this. They're unique like a fingerprint. Just like we can use fingerprints to identify people, we can use the emission spectra to identify the elements. So just showing you a couple more. We're going to do a lab where we're going to put chemicals into a Bunsen burner flame. And when we do that, the flame is going to give the atom energy. The electrons will go up to a higher level. They don't want to stay there because of Aufbau's principle. They want to come back down to the lowest level. They come back down, and when they do, they release their colorful light, and they will be unique to the elements. So for example, copper is always kind of a greenish color. Strontium is so pretty, it's a bright pink. Calcium is kind of a reddish orange. Potassium is really pretty, it's like a really light violet color. So we'll be able to identify what we're looking at based on the color that it gives off. This is the same way that fireworks work. The reason why fireworks are different colors is because they have some of these compounds in them, and the metal atoms inside the compound will absorb the energy from the explosion up in the air, and then when they go through the emission process and the electrons come back down to their lowest level, they release light in the visible range. And the neat thing is it's the metal atoms every time. For whatever reason, they're the ones that have just the perfect wavelengths coming out for us to be able to see them. So that's how they can design fireworks with different colors. One real quick thing, because of the nature of stars being far away from us and what stars are made of, we can't measure their spectrums the same way. So in the lab during our flame test, we're going to have hot chemicals inside the flame, right? A really, really hot gas inside the flame. It can be put through a prism. The prism will split the light into individual lines, and then we look at that. Absorption is a little bit different because what's happening is here's the star burning inside, right? And there's cold gas between the star and us. And so the outside of the star has this cold gas with all these elements in it. And so that will absorb energy on its way out towards us. Comes through the prism, and what ends up happening is instead of seeing colorful lines, we see these like this general color band spectrum, like a big rainbow, and black lines are showing up. And the black lines are what the cold gas, which wavelengths it absorbed. And so it will be like the reverse of the emission spectra, they're opposites. So this is what's getting sent out, this is what the cold gas is absorbing. Either way, we can get the same exact information. It's just that they're going to look like inverses of each other because, you know, with the star being way out in outer space, it's a little bit different than if we're just working in the lab with our Bunsen burner. So this is what a star spectra would look like, right? Is that we would see the rainbow band and then we would see the black lines. And you would look for the black lines in the same places as you would the normal emission spectra lines. So here are two stars, okay? So you can see this top one has tons and tons of little black stripes mixed in everywhere. And that's because there's tons and tons and tons of elements that have been made as the star burns up its fuel. That means this is a very old star. It may explode soon, right? It may become unstable when it runs out of fuel. This one on the bottom, there are some dark lines, but not nearly as many. And that's because there's not very many elements made. That tells them that this star is much, much younger, okay? So it's a pretty, specific example learning about the stars. They do think it's good for you to just have an awareness of how we know what's out there in the universe. It is a pretty interesting thing to learn about. If you want more detailed information or something here kind of sparked your curiosity, there's lots of really great documentaries by companies like Nova, PBS. They make some great documentaries about astronomy and outer space and things like that. And you can find a lot of those online for free. You're welcome to ask me questions. Not sure I'll have the answers, right? The part that I know, the part that's really the chemistry part, is this part, right? Knowing that the electrons are in orbitals and they want to be in the lowest one, knowing that they get boosted up during absorption, they fall back down during emission, they release their energy. If we're lucky, we see it in this visible spectrum, right? And that it's unique like a fingerprint. That's the chemistry part of it, okay? So that's the part we're going to focus on when we do our flame test later. All right, everybody, that was it for this video. Hope that was helpful. Bye.